Hello and welcome to the AICE Chemistry lecture series. In this video, we are going to look at section 5 of chapter 14, which is going to cover structural isomers. And it's going to introduce our first of two sections on isomerism and what isomers are, what isomerism is, and how it applies to organic chemistry. So what are structural isomers, or isomers in general, right? Different compounds may share the same chemical formulas, and we call these isomers. So an isomer is simply a compound that shares the same chemical formula as another compound, but is indeed a different compound. So for example, here we have two different compounds, and these are isomers of each other. Why? At the top we have propene, with 3 carbons, so again prop, double bond, this will be propene. And then in the bottom we have cyclopropane, right? So cyclopropane is a cyclical, it's a ring of 3 carbons, whereas propene is a linear unbranched hydrocarbon with a double bond, making it an alkene. These are two very different compounds. They have very different chemical reactions. They do not behave the same way. However, both of these compounds have 3 carbons and 6 hydrogens, giving them the exact same chemical formula. So C3H6, and this is why we don't usually use chemical formulas in organic chemistry, C3H6 could refer to either propene or cyclopropane. And those are two very different things, right? You do chemical reactions with these two, you get very different results. But they still have the same chemical formula. That's what makes them isomers of each other. These are isomers of each other because they're different compounds with the same chemical formula. Now, there's a lot of different types of isomers. The first type of isomer we're going to talk about, and we're going to focus on this section, is the umbrella term structural isomers. So what are structural isomers? Structural isomers are compounds with the same molecular formula, so that just makes them isomers, but different structural formulas. So the structural formula, if we draw it out, would be different. And these two, for example, are structural isomers, because if we did their structural formula, we will have very different results. For cyclopropene, or for propene, it will be I'm writing with the wrong color. It will be CH3, CH double bond CH2, whereas the structural formula for cyclopropane would be CH2, 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 because it, and then the fact that there's CH2 shows us that it's cyclical. So we have here propene, cyclopropane, different structural formulas. So these are structural isomers. There are 3 different types of structural isomers. Like I said, structural isomers are an umbrella term. There are 3 different structural isomer types that we're going to go through one by one. There are position isomers, functional group isomers, and chain isomers. Now remember, because all of these are isomers, right? Because position isomer, or positional, depending on who you ask, functional group isomers, chain isomers, because they're all isomers, they're all going to have the same molecular formula or chemical formula, right? They're all going to have the same chemical / molecular formula, but they're going to differ in how their structural formulas differ. Right, because these are all structural isomers. Their structural formulas will be different, but the way in which it's different is what changes from one type of structural isomer to another. So let's look at the specifics here for each one of these. And we're going to go through them one by one. So let's start with position isomers. Position isomers are probably the simplest of all the isomers to understand. Position isomers are simply compounds that have the same molecular formula. So again, anytime we have the definition of an isomer, which you will be asked to write down, so make sure that you understand what the definition of an isomer is. anytime we have an isomer, they're always going to have the same molecular formula. That's what makes them isomers. Otherwise, it wouldn't be isomers. What's going to change is why they are different. So in this case, the difference for position isomers is the position of a functional group. So in positional isomers or position isomers, the position part comes from the fact that the position of the functional group is going to be different. They don't have the same molecular formula because of the isomer, they're isomers, and because they're position isomers, the location of the functional group is different. So for example, if we look at all four of these molecules here in the center, all four of these molecules are positional isomers of each other. Each one of these molecules has 2 bromines, 6 hydrogens, and 3 carbons. But the bromines are going to play musical chairs. They change. The 2 bromines in this first molecule are in carbons 1 and 2. The bromines in the second molecule in carbons 2 and 3. Actually, let me number these so it's easier to visualize. So here are carbon 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So in the first one, like we said, the 2 bromines are in carbons 1 and 2. In the second one, the bromines are in carbons 1 and 3. In the third one, the bromines are in carbons 1, both of them. And in the fourth one, both of the bromines are in carbons 2. So because the general structure is the same, 3 carbons, 6 hydrogens, 2 bromines, but the position of those bromines is changing from molecule to molecule, all 4 of these molecules become positional isomers of each other. They all have the same chemical molecular formula, which is why they're isomers, but because the position changes, they're all different molecules. Now, if we were to name these, they actually will have all different names. This right here, oops, let me change the size of this marker. So this one, the first one, would be 1, 2 dibromopropane, because we have the 2 bromines, dibromo, in the first and second carbon, and it's propane because we have 3 carbons. This will be 1, 3 dibromo, propane. This will be 1, 1 dibromo propane. And this will be 2, 2 dibromo propane. So all 4 different compounds, we can see it in their name, but they are positional isomers of each other. We do need to be careful that we do not copy the same structure when we write positional isomers, because you will be asked, for example, we might be given this chemical formula and be asked, draw all of the positional isomers of this compound. And you will need to be careful you do not draw the same isomer twice. So for example, if we look down here, you got to remember that these carbons are single bonded, meaning that all of these carbon-carbon single bonds can rotate. So the position of this hydrogen, and the bromine doesn't quite matter. That means that this compound right here, this compound right here, and this compound right here are actually exactly the same. Whether I put that bromine in the top or that bromine on the side, that bromine is still in carbon 1. So these 2 compounds are actually exactly the same compound. They're not isomers of each other. Additionally, we need to remember that the whole molecule can be rotated. So we won't need to draw it as a line. We could draw it as an L. We could bend this. So this is carbon 1 and carbon 2 that have bromines. If we bend that molecule, it's still carbon 1 and carbon 2 that have the bromines in them. So because of that, this molecule in the middle and this molecule on the right are the exact same molecule. So you gotta be very careful when you draw organic compounds that you're not drawing, especially if you're trying to draw isomers, that you're not drawing the same molecule twice. And that happens a lot. It's one of the issues with visualization in organic chemistry, and one of the reasons why, if your brain is a little better at visualizing things, naturally, just because of how it works, you will be better at organic chemistry than the other forms of chemistry. Whereas if you struggle with visualization, it's not something come naturally to you, you're going to find this a little more difficult than you did, say, in organic or physical chemistry. So let's keep going. So this is position isomers. There's two other types of structural isomers. The next is functional group isomer. And this one's pretty straightforward. I mean, the name itself gives it away. A functional group isomer, again, they're going to have the same molecular formulas, and that just comes from the fact that they're isomers. So if they're isomers, they'll have the same molecular formula. What changes here is that they contain different functional groups. So that, if you didn't see that coming, that's pretty obvious, right? Functional group isomers contain different functional groups, even though they have the same structure. This is primarily going to happen whenever oxygen is present in a molecule, because there's so many different functional groups that have oxygen. The ones that we've seen, esters, carboxylic acids, aldehydes, ketones, alcohols, all have oxygen in them. And then there are some that we didn't even look at, like this right here. This is called ether. An ether might not be in your curriculum, but ethers are also a functional group. And they're a functional group with oxygen in them. So we could have something like this, where we have C3H8O, right, which will be an alcohol, or could be an alcohol, propan 1O, for example, 3 carbons, 8 hydrogens, and 1 oxygen. But we could actually rearrange that into an ether, so this is an alcohol. We could rearrange that into an ether where the oxygen serves as a bridge between carbon chains. That's what an ether is. It's an oxygen bridge that bridges 2 different carbon chains. This will be methoxymethane. You don't need to know how to name this, but this is a functional group isomer of propan 1O, because we still have 3 carbons, 1 oxygen, and 8 hydrogens, but now we have an ether instead of an alcohol. So these are functional group isomers of each other. These are a little more straightforward, more simple. Essentially, anytime you have an alcohol, you can form an ether. And there's a few other compounds that you may be able to form. One of the things you got to realize, though, is that if you have an alcohol, then the only other functional groups you can make are the ones with single bonds. Because if you make a double bond, that will get rid of this hydrogen. So if we were to double bond this oxygen, that oxygen will no longer be able to have this bond, so you will be getting rid of a hydrogen. So you would not have an isomer because the chemical formula would be different. So usually alcohols can isomer or functional group isomer with ethers, whereas things with double bonds can functional group with each other, like an aldehyde might become a ketone, and so on and so forth. So yeah, that's a functional group isomer. Again, oxygen is usually what brings these about. But they're isomers, so they have the same formulas, but because they're functional group isomers, they contain different functional groups. And so their structural formula would also be different, as they are a type of structural isomer. Here, the structural formula for this alcohol, for propan 1O, would be CH2OH, CH2, CH3. Whereas the formula for methoxyethane will be CH3O, CH2, CH3. So different structural formulas, which is why functional groups isomers are a subsection of structural isomers, just like positional isomers were. The last type of structural isomer we're going to look at is a chain isomer. Now, chain isomers are probably the most annoying whenever you get asked the question, draw all of the isomers for a structure. Chain isomers are annoying because they deal with the carbon backbone. So again, these are going to be isomers. So we are always going to have the fact that the compounds have the same molecular formula because they are, again, isomers. But chain isomers, the chain part is where they are different. A chain isomer differs in the structure of their carbon backbone, in the structure of the carbon skeleton, and in which way it splits and separates. So the carbon backbone of a chain isomer is different. The larger the number of carbons because of this, the more isomers a compound can have. So the more carbons there are in a chemical formula, the larger the number of chain isomers you will have. Additional elements like oxygen also create other isomers and can bring in things like functional group isomers and positional isomers. For example, if we have C4H10, C4H10 has two different chain isomers to it. There's N-butane, or what we just call butane, and there's what we call isobutane, but the proper name you will use will be 2-methylpropane. So why are these different? These are different because in isobutane, sorry, it's not isobutane, in butane, we have a straight carbon chain that does not branch. So we just have our 4 carbons in a row with the hydrogens on them. Whereas in 2-methylpropane, we have a carbon chain of 3 with a side chain that comes out of it. So it's different from the 2-methylpropane in its structural formula, which is why they're structural isomers. And the chain of carbons is Y, which specifically makes them a chain isomer. If we were to draw the structural formulas for this, we would have, for butane, we will have CH3, CH2, CH2, CH3, whereas for 2-methylpropane, we will have CH3, CH, CH3 in parentheses because that's a side chain, CH3. Or another way to draw this, because we have 2 CH3s here, is that we could just say CH, CH3, 2. And we will get rid of this CH3 here. And that's because we have 2 CH3s coming out of this carbon right here. That's just another way of drawing the structural formula. Both of them are correct. You could do either or. But that's why these are chain isomers, because their carbon backbone is different, but they both still have 4 carbons and 10 hydrogens. As you can see, as we increase the number of carbons, we get more chain isomers. So for example, in the case of C5H12, where we have added 1 carbon and 2 hydrogens, we can have now even more. We could have pentane, which is just a straight chain isomer, where we have the 5 carbons in a row. We could have 2-methylbutane, which is when we have 4 carbons in a row, and then a methyl side chain that comes out of that. And we could have 2,2-dimethylpropane, where we have 3 carbons in a row, and then 2 methyl side chains that come out of that. 1, 2. So these are all chain isomers of each other because we have the same chemical formula, C5H12, but their carbon backbone is arranged differently. Now, these do have some common names like isopentane, neopentane, and N-pentane. Do not worry about those names. In our form of nomenclature, we would just call this pentane, this 2-methylpentane or butane, and then 2,2-dimethylpropane, which is the proper IUPAC name. These other ones are just common names or a different type of nomenclature. So that's why these are chain isomers of each other. The more compounds or the more carbons we add to the compound, the more complex these get. Now, the worst kind of questions for isomerism is draw all of the structural isomers or draw all of the isomers for a specific compound. So, for example, let's do one of those. Let's just take a crack at it. Oops. So let's say we are asked to draw all of the isomers of C6H11Br. This is a gargantuan process. Now, you might not get something that's difficult on the AICE exam, but you have to consider all types of, in this case, structural isomers if we're asked to draw the structural isomers here. So the best way to do this, in my opinion, is to use skeletal formulas. So we'll have 6 carbons with a bromine. So we'll start with positional isomers. So we have 1, 2, 3, 4, 5, 6 carbons with a bromine. So that bromine could be on the first carbon, making it 1 bromohexane. We could have the bromine on the second carbon. So 1, 2, 3, 4, 5, 6 with a bromine on the second carbon. And that will be 2 bromohexane. We could have the bromine on the third carbon. So 1, 2, 3, 4, 5, 6. And put that bromine on the third carbon, which will be 3 bromohexane. And then this is where you have to stop yourself, because you might be tempted to say, okay, we could have it on the fourth carbon, right? 1, 2, 3, 4, 5, 6, and put that bromine on the fourth carbon. But this is actually not an isomer. These two compounds are actually the same. If you grab this compound and you flip it 180 degrees, you get this compound. Because if we start counting from here, yeah, this 1, 2, third carbon. But if we start counting from here, 1, 2, third carbon. So these are both 3 bromohexane. If you're ever in doubt as to whether two compounds are the same or not, name them. If you end up with the same name, they're the same compound. So this wouldn't be an isomer there. So that's the positional isomers. So these are all positional isomers of each other. That's the first thing we consider. The next thing we consider is where we can have any functional group isomers. Well, luckily for us, because these are bromines, not oxygens, we can't have a functional group isomer. So then we go into chain isomers. So we start moving this around. My recommendation, grab a stick, put it somewhere else. So make sure we always have the same number of carbons. So 1, 2, 3, 4, 5. And then that last carbon, the last stick, we're going to put somewhere else. So that's that right there. So we make this backbone and then we play around with that bromine. So first of all, we could have this isomer right here. That will be 1, 2, 3, 4, 5. That will be 5 brom or 2-methyl 5-bromo pentane. We move the bromine over again, so we keep the same structure. 1, 2, 3, 4, 5 with a stick. And then we move the bromine. That will be 1, 2, 3, 4 bromo, and then this is 2-methyl, so 2-methyl, 4 bromo, 2-methyl pentane, different compound. We can move the bromine again and put it in the bottom. So that would be, oops, I forgot my methyl. So this will be 3 bromo, 2-methyl pentane. We could move, again, that bromine to where our methyl is. Because remember, this carbon can have up to 4 bonds. So we could put that bromine here. Br. And this will be 2 bromo, 2-methyl pentane. And we can actually do one more and put that bromine, 1, 2, 3, 4, 5. Notice how I'm leaving a lot of empty space because I don't know where this ends, right? We're just going to keep going until it does. I could put that bromine on the first carbon. Now you might be saying, Mr. Pendola, why would we do that when we already put it on the carbon at the end here? Well, because of this methyl group, that bromine, those carbons are actually different. Because this one is right next to the methyl, this one is not. So this is actually a different compound. This will be 1 bromo, 2-methyl pentane, whereas this is 5 bromo, 2-methyl pentane. So these are different compounds. what we don't want to do is that you might be tempted to say, okay, I can put that bromine on that methyl group. I can put that bromine at the top. And you might think that this is a different compound. But remember, this bond can rotate, meaning whether we put the bromine here or here, it is still one carbon away from the methyl. So this is also 1-bromo-2-methyl-pentane, just like this. So these are the same compound. This is not a different isomer. And then we can go on. The more, like I said, the more carbons we have, the more functional groups we have, the more complex this gets. We can now grab that methyl group and put it in that central carbon, in carbon number 3. So we could have this 1, 2, 3, 4, 5 with our 6 carbon here. And then again, we can play around with that bromine. So we could have the bromine here. And this will be 1-bromo-3-methyl-pentane. We could put, and I'm just going to draw a few of these so I can expedite this process. I think 4 of them should be fine. I could move that bromine here. And this will be 2-bromo-3-methyl-pentane. I would not be able to put this bromine here because this being symmetrical will give me the same compound. I could put that bromine here and give me 3-bromo-3-methyl-pentane. Or I could put that bromine here, which would give me, because we need to include that bromine in the main chain, will give me 1-bromo-2-ethyl-butane, because we have 4 carbons here. So, then we create another chain isomer. We can move more of these. So if we make our main chain 4 carbons instead, we could put a methyl group here and a methyl group here. And if we do that, we can actually have 2 different positional isomers. We could have our bromine at the end of a carbon, Br, and then whether it's this one, this one, this one, or this one, it wouldn't matter. It will still be 1-bromo, 2-methyl, 3-methyl, or dimethyl, 2,3-dimethyl butane. Or we could put that bromine here in one of these central carbons and have 2-bromo, 2,3-dimethyl butane. Now we do gotta make sure that we do not repeat these, that we're not accidentally repeating some compounds here. We wouldn't put an ethyl somewhere in there. Actually, we might be able to. So we might be able to grab both of these methyls and make an ethyl, but that would just recreate this compound right here. Because notice 1, 2, 3, 4, 2 carbons will be this compound right here. And then if we used 3 carbons, let's see if we can do something with that. That will be 3. And then we could do 4, 5. I don't think we have this one yet. So 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4 with 2 methyls on the same one. 1, 2, 3, 4 with 2 methyls. And yeah, so we don't have this one yet. Now we can play around with this one. And I believe we can make 2 positional isomers out of this. 1 here, actually 3. And we can put the bromine either at the end of the long chain, second in from the long chain, or on one of our methyls here. And I believe that will be 3 different compounds. So again, this takes a lot of time. It takes a lot of practice because you have to make sure that none of these molecules are actually the same molecule. You have to make sure that none of these molecules are identical to each other, because that might lead you to have a wrong compound. So, or a wrong answer. Again, this is a very intense question because we will have 6 carbons and a bromine. How we put an oxygen in there, it would have been even worse because then we could have brought in functional group isomers. But there are questions in the AICE exam where you're asked to draw every type of isomer, every structural isomer, every chain isomer, or every positional isomer of a specific structure or formula. So this is just how we can apply what we just learned about the different kinds of structural isomerism here. And I might have missed one here. I don't believe I did, but again, I could have missed one. It is kind of how the isomers questions go, where you're never sure when you're done. But yeah, that's it. That's it for functional isomers in this section. We're going to cover stereoisomers in the next section, which is a completely different type of isomer. Until then, I will see you in the next video.